We now move to the second issue of the theoretical part of this talk, that of epidemic models for the dissemination of information in a network. There are several such models, and we shall classify them according to two criteria: the virality and the size of the population. For the size of the population, we shall consider either a fixed target population, or an unbounded one, or one which is finite but increases in time. By virality, we mean the following. A content is said to be viral if the network participates in a substantial way in the dissemination of information. In that case, the probability that someone who has not seen yet a content will see it within some interval of time t increases in time. The first model you will consider is a linear growth model due to immigration. There is only an external source of demand for content. The network doesn't help to generate more demand. If the immigration process is ergodic, then the number of views grows linearly. I will show several examples that fall into the category of contemporary classical music. The first one is a piece for 9 cellos. So we see a linear increasing curve over a period of a year that reached more than 2 million listeners or viewers. A second example is Webern, and we see here a linear growth over a period of 5 years, between 2007 and 2012. Here is finally a piece of Pierre Boulez, who is also the director of the orchestra. Also, we see here linear growth over a period of 5 years. Next, I introduce another class of videos that have a linear growth. I call these disappointing videos. The first example is a video by my friend Julio Rojas, whose title is "Dragons Do Exist." In this video, Julio tries to prove that his friend snores at night when he sleeps. So the content of the video is just audio snoring. There is a nice title and a nice picture that attract people to listen and to watch this video, but once they listen to it, they're not enthusiastic sufficient in order to share it or to embed it, and thus to create a viral process of demand for this video. It is this disappointment that explains why we don't have a viral process of people who get to know about this through the network. To check that this is indeed a disappointing video, we can just have a look at the likes and dislikes. There are 3 times more dislikes than likes. Here is probably the most popular video among the unpopular ones, so among the disappointing ones. So it has also a linear growth as the previous one had. And again, it has many more dislikes than likes. And still it is quite popular because it had around 40 million viewers. But probably most of these didn't share this video, were not keen on propagating it to their friends. So again, the network did not have a viral effect on this video. We next introduce branching models that can give rise to either a concave or to a convex behavior of the view count. The simplest branching process is described by a process of generation. The process of interest is how many individuals are in the nth generation. And this number is given recursively. It is the sum of the offsprings of all those that lived in the previous generation. Each one of them gives a number of offspring that is distributed like a random variable that is called z here. The branching process is called supercritical if r is greater than 1, and is otherwise called subcritical. Here are 3 examples of YouTube music that give rise to a convex increasing view count over a large period of time. All 3 of them are classical music that are well known, that are quite popular. So the first one is Tchaikovsky's music, the second one is music by Schubert, and the third one is music by Mozart. Unlike music that we saw before, contemporary music that had linear growth, here we have a viral effect that is due to the influence of the network, to the fact that people do discover things thanks to recommendations and do recommend themselves or share music, classical popular music. The concave increasing model that we saw in the branching process indeed gave rise to concave curves, but for very special ones, curves that converge to a constant. This means that there is a constant interested potential group of people, and when they're all reached, then there'll be no more dissemination in the network. An alternative model is a combination of that model and the linear increasing model. So once most of those who are interested received the file of interest or the content of interest, there still is an increase, a constant increase in the number of viewers. This is a phenomenon that we do observe, and it can be described mathematically using branching process with an extra term Bn, which is an amount that arrives at the end generation from the outside. It is called immigration term. In the next slide, we have an example of this behavior. We see that after a very concave beginning, there is a convergence to a constant rate of increase. Another example is the inauguration speech of President Barack Obama in 2009. You see that it is very concave in the beginning, and then it doesn't converge to a constant, but increases at a constant rate. We found the same in a song that President Obama was singing in Chicago, Sweet Home Chicago. It gave rise to an exponential increasing view count, a concave one, so it is a subcritical regime, plus a linear asymptote to which it converges. We now introduce epidemic models. In branching, one assumes that the distribution of the number of offsprings does not depend on the population size. So basically, it is appropriate for unbounded population size. In practice, the population may be limited, and thus the more there are infected, the smaller is the probability for new infected ones. Here's a very popular model for the dissemination of information. The rate at which the number of infected users increase in time is proportional to the product of those that carry information, this is the x, times those that are not yet infected. So in terms of fraction of infected, those or not infected, this gives the 1 minus x. Thus we have the product between x and 1 minus x. Now the solution of this differential equation is quite simple. We divide both sides by x times 1 minus x, and then rewrite this product as the summation of 1 over x plus 1 over 1 minus x. We now integrate both sides of this equation and get that this difference between two logarithmic terms equals kt. We then take the exponential in both sides of the equation and obtain a simple expression for x of t. This type of dynamics creates first a viral part, a part in which the view count increases exponentially fast, and then it gradually becomes more and more flat as the number of infected grows. And of course, whenever one is infected, then it remains constant. It is thus a combination of a concave and a convex part. So here is an example of a viral and a non-viral video. We see that in the right-hand side, the beginning is very convex, so that part is viral. Whereas in the left-hand side, it is concave at the beginning. In fact, everywhere it is concave. And thus it is not viral. And here are other examples. This is a young boy that plays marvelously the violin. And then there is Gangnam Style, which is very well known, which got already more than 1.5 billion views, where we see that there is initially a convex increasing part of the view count, and then the view count becomes slowly more and more flat, more and more concave. In the epidemic model, we assume that each one of the nodes which is contaminated can further contaminate other ones. Now, if only the source can contaminate, and if we have a finite population size, which we normalize to 1 as before, then the equation that we get is just that the rate of increase in the number of contaminated is proportional to the number of non-contaminated users. So this gives us an exponential model again, just as we had in the branching process. We have a concave increasing curve for the number of views. It is parametrized by the rate at the beginning, which is this m. So this is what we get for different initial states. So we see in all cases we get the concave function. We cannot distinguish between the case of finite population, which we have here, and with the case of infinite, which we had in the branching process. So an infinite population, but with small r, gives the same behavior as this model with finite population. To conclude, we studied 4 models: a linear one, a convex viral one, a concave one, and one that combines first phase which is convex and then a phase which is concave. The models that were considered were branching process models, as well as an epidemic spreading model. We further considered the combination of one of these models with a linear asymptotics, in which case we had a convergence to this linear asymptotics instead of a convergence to a constant. From our experience, these models indeed cover the majority of behaviors that we observe on YouTube. The various models will be used later to construct models for advertisement in social networks, but can also be used in order to predict the evolution of popularity of a video.